So here we're just finishing off where we stopped in the last video. This is the latest value we calculated for x in the NewtonRaphson iteration method. So plug it in the equation for f of x, plug it in f prime of x, and you get this. So we're now pretty much almost converged, right? Because the correct answer is 2. So use that in those places. Again, new value. Just keep doing this iteratively, and eventually you have this. So I don't like to set this kind of question in the exam where you go multiple times, right? But what I can easily do is to set it up and give you one initial condition and have you do it one step. Because if you can do it one step, you can do it multiple times. So don't assume this can't be tested. I actually would like to make you learn this skill because it's very useful. And before we go to the next section, which talks about second method, I'd like to point out that even though we've set it up for single values, right? We will later talk more about this when we start doing multi-phase non-linear problems, because Newton-Raphson is very powerful. That's what we use in those cases. And in those cases, we are not going to be solving for single values. We're going to be setting up residual for all of the equations together. So back to what we did before, right? This was what we did for the Taylor series expansion. F prime, right? Then square that and divide by 2 factorial f prime prime x. This is what we did before for single values. Well, and we said we're going to forget about this for a minute. We can do this again for where this is a vector. So what is going to change is the fact that, so all of these are vectors, and this is really delta x, and it's a vector, right? What is going to change is the fact that this derivative is going to give you a matrix. When you differentiate a variable, let's say f of x is f of x1, x2, x3. So x is a vector, right? Like you see there. Well, when you want to differentiate it, what are you going to differentiate it with respect to? With respect to x, right? But x is a vector. So what you're going to end up getting for f prime of x will be a matrix of derivatives. It's going to be the derivative of f of at x1, right? With respect to x1, then the derivative of x1 with respect to x2, and finally derivative of x1 with respect to x3. Do that again. This time around it's x2. You're differentiating x2 with respect to what? x1, x2, and x3. Finally, x3, right? You're differentiating x3, f of x3 with respect to what? x1, x2, and x3. And this is a matrix of derivatives, which is called Jacobian. So this is the approach we typically use when your equation is non-linear. Remember we said the equation we derived, which is the continuity equation after substituting in Darcy equation, was non-linear. it was precisely this. Del dot, as the divergence of rho, this is going to become plus because we're substituting in that, which has a negative sign, all right, equals 0 if there are no sources of sink. So this equation is nonlinear because these guys are functions of pressure. So to linearize this equation, the way we set it up is after discretizing with respect to time and space using finite differencing, we will take all the terms to one side, and instead of it being 0, it's going to be residual on the right hand side, right? And that residual, you will realize, is going to be your f, and the derivative of the f is going to be your Jacobian, which we like to represent by J. So what does this translate to in vector form? This is your latest value of residual, which will be 0, right? Just like this, we're looking for the root of the function. This is 0. This will be your residual. Like I said, the function is going to be the residual. It's basically this term equals residual after discretizing. So you have done the n plus 1 minus the n, right? N plus 1 minus n for the time step. And for this, you have used the central difference approximation for the second order term. So it can't be 0 because of truncation error is equal to the residual. So your f is actually your residual at the previous time step. So n. This one is n plus 1, which is 0, plus delta x, right? Which is x minus xn. That's what your delta x is. And now, instead of f prime x is what? Your Jacobian. And we actually write the Jacobian before the delta x. So it's Jacobian multiplied by delta x because it's a matrix vector multiplication. So the Jacobian has to come before the delta x. And what do we do next? This is what you're looking for. So make that the subject of the equation. Take minus r to the other side. So we can rewrite it in this form, right? Minus r. So this is in the form of ax equals b, which we have talked about before, right? So the way you solve it is to take the transpose, pre-multiply both sides by Jacobian inverse, which, like I explained before, is as simple as doing Jacobian backslash minus r at n in MATLAB. And so the solution will give you delta x's. You would have assumed an xn, right, like we did before. So you start out with xn, you get delta x, then you make xn plus 1 your previous plus the change in x, and you update this guy, and you repeat that again. Use this solution in the next xn plus 1 after solving for delta x, and you keep doing that until you convert. Just showing you what it looks like in matrix form. And after this, we'll move on and discuss the second method. Good.